Okay, sorry for being late. Here's some echo. Do you have echo? Okay, did you turn it off? Okay. Sorry for coming late. I was in Taipei City for a meeting in Taiwan that we have different government organization. One of the organization responsible for provide research funding for most of the universities called the National Science Council, Science and Technology Council, NSTC. Okay, and they have recently announced a big AI project, and we submitted a project, and today we went to kind of give a report on what we wanted to do, and there was a committee, so I needed to be there. We don't know whether we will get the funding or not. If we get the funding, it means that we have more things that we need to do. If we don't get the funding, we won't have money. So it's a hard choice always, all the time, that whether you go for some research funding or not. Okay. In any case, I hope that now you are able to use the AI platform and you have the account. You can upload your program or you can use the VS Code in the platform. You can write your program. I think that there's some default setting for every student, how many GPU they can use. Just one, right? But on the other hand, you have some memory and you can, it's a pretty powerful GPU, so you can use that to write some pretty decent size program. So the example code that we have given you is this code, which is if you, I know that you actually have a copy, you may have already run it, but actually it's just a very simple converter between the degree, the Celsius and Fahrenheit. So we were given some numbers. I think there were 10 numbers, and these are the degrees in Celsius first. Okay, and it's trying to see that from this, and you have this is going to be your correct answer, and see that whether you can use the system to train to try to find the model. Eventually will be able to convert between Celsius and Fahrenheit. Of course, we know that there's a mathematical formula that you can use to do the conversion. Okay, but on the other hand, that the idea of using AI is that you don't need to have any knowledge at all, no specific domain knowledge. You were just given a lot of input data, okay, and you also are given supposed to be the correct answer, and you try to use AI to figure out the relationship, which is this particular model here, the three numbers, the W, and you have the B, okay, and then you might have some, I'm sorry, I know the system, no. Okay. Let's see that whether I'm well prepared. I have a brand new HDMI connected to see that whether this would work. Okay. Because this is the public classroom, so been used quite a lot to connect and disconnect, and sometimes the cable would become to be not so good. Okay, so bear with me for a second. Okay. Okay, so I'm going to share the screen. Okay, so this particular program is a very simple program, and we will talk about some of the theory behind it in the slide, but let me just kind of quickly go through this program structure. Okay, so you can see that, so we have the list, okay, or the tensor, which eventually is going to become to be a tensor when you try to use the PyTorch. So originally it was T underscore C was, it is actually defined to be a list in Python, right? But every time when you want to run that in the PyTorch, you need to have the specific operation here to convert that into a tensor, okay? So even though in here, they use exactly the same name, but if you try to look at the type, okay, inside of the your notebook or something, then you will see that this T underscore C originally is simply a Python list. But here, after we have done this torch.tensor, then this T underscore C become to be a PyTorch tensor. Okay, PyTorch tensor now, inside of the, when you use a PyTorch, you will understand this is the data structure, and that particular data structure, it can be run locally, okay, as a tensor, or if you want to run that on the GPU, then you can, kind of use a command to say that I want to move the particular tensor or this particular data structure to your particular GPU. Okay, so these 4 lines is simply to define the tensor. Okay, then we have defined this model, and the model that we are trying to have PyTorch to train is simply to have T underscore U. This is going to be the tensor for this U here, and this U here you can see in real world is the degree Fahrenheit, right? And so we'll be giving them the tensor, the degree in Fahrenheit, okay? And we'll try to learn these 2 parameters, W and B, okay? And we will see in this, the slide I talk about later, and this is actually going to be a matrix, okay? And this matrix is something that we are going to, sometimes we call them to be the parameters in the model, okay? And B is the bias, okay? We'll talk about this in the slide. And you can also, it defines a loss function. And the loss function simply is that once we have the model trained, whenever we give the degree, the T underscore U, then the model will predict what is the output. And that particular output is going to be T underscore P, the prediction, right? And so the prediction, and the T underscore C, you can see that will be the original in the sources, the degree in sources. So the loss function will try to compare the prediction from the model and the correct answer, because we know these are the correct answers for those degrees. And so you just take these two, and you can see that this one here defines a very simple loss function, which is simply the square of the difference, okay? And the square of difference, so therefore that this particular loss function, it will be just taking the 2 values and to do the difference and then square, okay? And then you will return this. And so both the model and the loss function can be something you can change, okay? And I don't know with this program whether it has some different loss function or yeah, probably not. This is a very simple program. It's simply just try to show you the different training phase, but sometimes that you can see that here it says that the model, okay, and this model here you can actually define it to be something different, okay. So initially we don't know what is supposed to be the correct W and B. Okay, so we simply set W and B to be torched out once, means that we're going to set everything to a value of 1, and the torch B here, the value B here, we simply say this is going to be the zeros. Okay, so bias is going to be 0. okay, and then the W is going to be initialized to 1, okay, whatever is going to be the sign. And then you can see that we simply, can send it to model and then give this initial TU and W and B, and you will produce a prediction. Okay, so we already defined this model here, and you will produce a prediction. And if you run it, then you're going to see that what is going to be the actual numbers predicted, okay, given the input, which is going to be the TU, okay? After that, we define the loss, and you can see the loss is going to be calling this particular loss function, and you'll be using the value which you have predicted, given the state of the input, okay, and the correct answer. And you can see that will be the loss. Okay, so that's the way. Suppose that you have a correct model, and then this loss function here will tell you how good is your prediction. Okay, and so this is simply just to say, okay, you can try to do this in this way, and all the other programs here simply just trying to say, okay, now we have this initial model which is zeros and ones, okay, and so we can now go into the training, and then we can try to see that how we can use the loss function, okay, because we know that the answer is incorrect, okay, and then we can try to use the loss function to decide how we want to change the value in W. W is the model that we are supposed to train, okay, the model is that we want to get it so that we will be able to minimize the loss function as much as we can. Initially, the loss function, you may be lucky, you may be not so lucky, because it's just initial randomly generated times some value, and so you can see that, okay, it's going to be something. And then there is a delta which is defined. Delta says that I'm going to try to see that, okay, from this model, okay, I get some particular loss value, okay, and then I also have another loss value given me, okay, with certain, kind of a difference between them, okay, divided by 2 times delta, means that how much of the difference in terms of the loss value that you want to use, okay, for you to be making the changes. Okay, so the delta here could be initially set to be 0.1. It means that whatever is the difference between these two values, okay, and these two values, let's see what's the difference. Let me see. Okay, one is going to be W plus delta, the other one is W minus delta. Okay, just a little bit of a change of the W, okay, and to see that how much, if I move the W to +1 and move the W, I'm sorry, the +1, plus 0.1, and the W, kind of under, to the other way, okay, and I'll try to see that divided by 2 times delta to see that how much of a difference would it make. So I move the W value to something bigger or something a little bit smaller, and see how much of the difference you will make. Okay, and then this is going to be trying to figure out, which I will talk about, in the when I'm talking about the gradient, and then from that, then we can say, well, this loss rate of change is going to be used really is to try to update the W. Okay, and so therefore that we will be using this loss rate of change times the learning rate, is how much of this information I find out. Whenever I change the W value, then it's going to produce some difference in terms of loss. Okay, but I may not want to take everything here to say that I'm going to change the W so aggressively. And so usually we will have something called learning rate. Learning rate just means that I know that if I move the W in this way, that you're going to see so much of the loss change. But, okay, that kind of a change maybe is too much. I want to do it slowly, so I will use a learning rate, which here is 1e minus 2. It's going to be e to minus 2 means that 1 over 100, right? And so therefore it's going to be 0.01, okay? That's going to be I know that if I change the value of the W in a certain way, you would create so much change. But I'm just going to make my W to move a little bit, change a little bit, okay, and see that how, whether it's going to be, making some difference. Because I have the computer and the computer can run forever, okay? So I'm just going to move slowly. I don't try to do it so aggressively. I don't try to say, oh, I think this is the right way and I move too much in that way. Because if I do that, and sometimes that, if you are, unfortunately, you are in a situation just like when you go into a certain road, then you may have overshoot. Okay, you have an overshot shot to something, and then you have to come back and this and that. So we just try to test a little bit to see that whether this is the right direction or not, and such and such. Okay, and so therefore this W will be changed a little bit. Okay, and then we'll continue to try to do this again and again. So that's kind of the basic idea, okay, of the training. Training is going to be saying that, we can define this way, and then we can have this training loop here. You can see that it's going to be doing this over and over again in terms of the epoch, how many times you want to try to change the update. Okay, so I'm going to skip the program for now, and let's just try to look at some of the slide. The slide I am taking, you can see who the authors, who are the teachers. Do you recognize the name? Fei-Fei Li. Fei-Fei Li, she is a professor at the Stanford University, and she was the original project creator of the ImageNet. Okay, and she is now a fellow member of the National Academy of Science, Academy of Engineering, and she is in all different kind of work. She is one of the most important persons for computer vision research. Okay, and so this was her lecture slide for her lecture in the Stanford University. Okay, so this is going to be using the idea of the computer vision to illustrate machine learning. Okay, but actually, after this week, maybe next week or something, then we'll start to really look into the computer vision as a set of topic. But here, I think it's easier for people to understand the idea of the machine learning, the neural network using computer visions. Okay, so suppose that we are trying to create a program which we can do the job, and this is called the image classification. Image classification is one category of the functions that we want to be able to ask the computer to do. Whenever they look at a picture, then they can tell me what's in here. Okay, and the ImageNet project actually has collected a lot of pictures from all over the world, and they are trying to use that set of images and then ask people to say, can you write a computer machine learning program which will be able to look at this picture and tell me the answer to say, this is cat in the picture. Well, the most important thing is going to be the cat in the picture. The cat is probably some of the background, but at least can you see that whether this is the picture. Okay, and the correct answer for the pictures, they're going to be a set of possible labels, including dog, cat, truck, plane, and many other things. Okay, but in this data set here, depending on which generation of data set, they could be, initially there were 10 different classes. They have a lot of picture. They have different type of things, but your system should produce the answer to say this is a cat. How do we recognize inside the picture there's a cat? As a human, how do you see that? We don't know. Really, we just look at picture and say, oh, there's a cat. It's so obvious, what the silly question. This is a cat, okay? But of course that for computers, actually what they see whenever they see a picture is what? It's a whole matrix of numbers, just numbers or pixels. This is what the computer sees, okay? So an image really is a tensor of integers, okay? In our computer vision, the idea is that every pixel will be given a number, okay? And that number is going to be what we call as the RGB code, okay? And so it could be one number or it could be three numbers, okay? When you have three numbers, it means you have the red, green, and blue, okay? When you have one number, it means it's gray. The gray label is how dark or how strong that particular pixel is, okay? But in any case, a picture will be read in to the computer to be simply a matrix of numbers. And the number, each of the value here will be a value 0 to 256 different levels of the darkness, okay? Or if it's RGB, okay, it means how much red it has, how much green it has, and how much blue it has, okay? And so normally, in the old days, we have a picture which is usually 800 by 600 pixels, not so high resolution. But now, of course, that our cameras are getting better. Our cell phone is getting, kind of more powerful, and so each picture actually now has more information. Okay. So when we try to build machine learning program, is simply, you can say, it's almost like the Python program we have just seen, the model. Okay, and this model here is called classify images. And then we simply enter or input the image, and then we expect it to be returning in some prediction to us. And this one is going to be the class label. Inside is going to be your code. Okay, whatever is going to be your model. Okay, and so that's how we do. Okay, so the computer vision is a field which has been around for a long time. At least more than 50 years. Okay, even before we have all this idea of the deep learning and other things, people have already been trying to understand pictures, okay, in using different type of computer technology. At that time, that computer vision is an area you can say that is part of the in the W we have the signal processing field, okay, or the information theory, that kind of thing. And they try to use many of the mathematical model. Okay, so they have been trying to say, for example, using some mathematical function to be able to calculate, given us this picture here, to find edges. Okay, edges means that you can see that in the body of this, okay, between this body of the cat and the background, there is a clear difference. Okay, clear difference. And so from all of these different lines or different kind of very sharp contrast in a picture, we can see there's going to be something like this. And for computer, this is something not as meaningful, but when we have something like this from your human eye, is this more meaningful than that? Well, we see the whole picture with a rich information, but for many of the computers programs, this actually is easier to try to process, because you can see this mathematically, we can define a lot of properties with a line, with a curve, with all this shape and things. We can try to use mathematical functions, okay, to define all these different things. And with different things here, maybe, okay, in the old technology is trying to put it together to say, well, if we have this shape, okay, with certain, things, certain curves, okay, it could be similar to an eye. If we have something like this, okay, then, it can be defined to say this is the shape of an ear, okay. But of course, you can say this in some pictures could be a shape of a small hill, okay, or it could be a leaf of a vegetable. right? It could be many different things. But hopefully, in the good, old days when using computer vision technology, by using the combinations of all these different particular shape, okay, then you can put it together to say, if the picture here has 2 ears or two such shape like ear, you have 2 eyes and you have certain textures, okay, then we can try to conclude to say that it should be a cat with a high probability could be a cat. Okay, and so definitely you can see that this is going to be something. It's going to take a lot of work because you have to do all the mathematical processing. Then you have to try to put all the possibilities together and then add them together and then come up with something. Okay, and then make a decision. Those were the technology used in the old computer vision, trying to do the prediction. So when you start to have a lot of pictures, a lot of different classes, not just cat, but maybe also tiger and the dog, okay, and maybe some other kind of animals, then sometimes it's very confusing. So the old computer vision technology is just simply, not always correct, okay, in making the prediction, okay, and you make a lot of mistakes, and sometimes also that depending on the size of the picture, okay, it's going to be too difficult to process when you have a picture with a lot of details, okay, because here we were talking about 800 by 600 pixels in a picture, and nowadays we have high resolution picture, we have 4K, we have getting more and more. And if you have some, kind of specific object which is very small, then also it's quite difficult to do. Okay, so later, okay, when the machine learning technology become to be more and more mature, we simply say, okay, how about this? Let's be lazy as human. Let's don't worry about it. Okay, let's try to find some algorithm or some mechanism. And if we can just give this to the computer and that computer try to understand by itself, okay, then it will be wonderful, right? Everybody will be happy. If the result can be correct. Okay? And that would be something that what the machine learning, trying to do. It doesn't try to define the specific features in order for us to make the prediction. It simply try to say, okay, we have a lot of information, and all this information, I'm going to let you see that just like the model we have just seen. Okay, we have a T W times something, okay, plus the B, and then just try to correct your W yourself as much as you can, and eventually, hopefully, that you can try to build this, and then after that, I can try to give you some extra images and see how good is your result. Okay, so here you can see that we define two different functions. One is to train, and the other one is to predict. And the image originally collected by Fei-Fei Li and other people is the ImageNet. But before that, actually, also there was another set of data people have used. It's called the MNIST. Okay, and this is actually handwriting pictures. It just collected a lot of different ways for us to be writing the numbers. Okay, each of this is, we know that human, again, we look at that, we know what is that particular number it is supposed to be. Okay, and so so each of these pictures is very easy for us to say what is going to be the correct result, and also to store this information. Each of them, it doesn't need to be color. It could be just grayscale. It could be just black and white. Okay, and also the pixel is much smaller. It's 28 by 28. Okay, And for this particular data set, we have 50,000 such handwritten numbers, and they can be used as a training set. Another 10,000 can be used to test it to see how good your model is. So for human, of course, sometimes we make mistakes because some of the writings are not so clear, like this one here. We can, of course, we probably agree that this is a 2, right? But this also could be something very close to 0. Okay, so between the 2 and 0, okay, and in this 2 here, you can see that they are not always so obvious. Okay, so this is one of the data sets, and the ImageNet, okay, which has been created for this 10 classes, okay, it's called CIFAR 10, okay, and the CIFAR 10, it has, the pictures are natural images, okay, and each of this natural image actually belong to one of the 10 classes, and you have a total of 50,000 training images, and we have 10,000 testing images. And each of the picture is originally set to be 32 by 32. Okay, so it's again not high resolution by the 32 by 32, but it's in color. Okay, 3 different color RGB. Okay, so this is the again very popular data set that people have used for the computer vision training. Later, the data set was expanded to be CIFAR 100, and in this one here that we expanded the class to have total of 100 different classes, okay, including could be human, could be car, could be building, and such. And the image, each specific one, okay, is still the same. And the number of training images per class is 500, and so therefore the total size of the picture is still the same, but now the class has included. It included some, aquatic mammals, beaver, dolphin, and such. You have tree, but not just tree, but also depending on the different type of tree, and this is something has been used. Okay. Later, another one is expand this one here to 1,000 classes when the computer now getting more and more powerful. And they have created this one here to be 1.3 million training data pictures, which means that each class you have about 1,300, 1.3 thousand pictures. And then, we have so many different pictures, okay, and also the so when you have so many different classes, okay, you have so many pictures, definitely that probably the algorithms, whatever algorithm, whatever model you trained, wouldn't be 100% correct. Okay, so it's not going to be just comparing to see how many of them you're correct, but actually right now we also use another performance metric, which is called top 5 accuracy. Okay, which means that algorithm can predict 5 labels for each of the class, and at least one of them need to be correct. Okay, so for each picture, you make prediction to say this could be one of the 5 possible class. As long as you have one of them to be correct, then we consider you are okay. Okay, just like human, that sometimes when I look at this one here, what do you say this is? This one? What do you see? Well, your answer could be human, right? Your answer could be dog. Your answer could be tree. So you could actually have many different predictions. And all of them could be correct. And that's why that they say that as long as one of them is correct, then at least you are not making it up, because your picture actually could have many different things in there. Okay? So top 5 accuracy is not so much of that we are relaxing your accuracy, but it's more your picture could become to be much more complicated. And when your picture are much more complicated, okay, there is no unique answer. Okay, and so top 5 accuracy, okay, later when you see this number, don't say that, oh, you are relaxing the correctness. No, because the richness of your picture actually is making the difference. Okay, and after that, now we have the ImageNet. Okay, and the ImageNet again is 1,000 classes, and you have so many training pictures, and you have this and that, and the image now has different sizes, and the variable size, but often they are kind of converted to 256 to 256 for training. So because when we train the system, your input is better to be all the same, because we are going to be using this big W, right? And this W here is going to try to, the tensor try to, kind of calculate, try to do the computation. And if your sizes are too different, then it's kind of difficult to try to produce the model. Okay. There is also 22K category version of the ImageNet. Okay, this is going to be much more than 1,000. Okay, 22,000 classes. Okay, which is, I think, in real life we probably see that, right? In our human eyes, that we can see pictures to have 22,000 different objects in there. Okay, we can recognize it, but it's not so much that you can not do that, but this one here become to be, the data size is quite big. Okay, so for you to be able to try to train your model, you need to have a much larger computer memories, and also you need to have faster things. Okay, MIT has produced another set which has 365 different scene types. Okay, it's no longer going to be about object, but actually it's going to be about different scene. Okay, like this is going to be a field, this is in a bar, and this is in a bedroom, and this is in a watering hole. I don't know what it's supposed to mean. Okay, but it just means that because some place it was with water, and people go there for something, and the fish pond. Okay, so anyway. So it has 365 different classes. And when you look at the picture, you try to predict to see that what type of scene out of the 365 it is probably most related to. Okay. In human eye, when you look at the scene, do you see only 365? We probably have more than that, right? I mean, human eye, our mind, when we look at this, okay, look out the window, what do you see? Look out the window. What do you see? Sky? Or from here, I see buildings, okay, or hills, okay? And if you were in the southern Taiwan 2 days ago, you probably see what? Wind. You don't really see wind, but you sense the wind, right? But in terms of the scene, sometimes it could be something like that, okay? What defines to be a bar? How do you define a bar? What are the most important ingredients? Alcohol or human? Or noise? But of course, in the picture, you won't see noise, right? Okay, but what do you see? When you say, okay, this is a bar, and if I give you another picture, which is a train station in India, can you see the difference? What would be the difference between a bar and a train station? With all due respect, okay, I'm not trying to make fun of something, but in train station, probably some people are lying on the floor. In a bar, sometimes, but not so often, right? Okay, in a classroom, in a movie theater, what will be the difference? Usually, in a classroom, some people will be sleeping. In a movie theater, usually not. people will be watching, most of the eyes will be wide open, right? So seeing definitely is a much more difficult to try to detect because it's not just matching the objects, but also there should be certain specific features or some combination of feature. And that's why that this MIT places actually is something quite difficult to do. And this one here was, in 2017 that they have produced this data set. Okay, so in any case, okay, what we're trying to do is to try to have, kind of a algorithm or machine learning program which will be able to look at the picture and make a prediction. Okay, we know what will be the correct answer. So, for example, this one here is supposed to be a cat, and if we already know some pictures from the original training data set, there are cats, there are cars, there are planes, and so how do we decide how close is this one to any of this? That would be what we call as the distance, okay? Or in our current definition would be like your loss function, your prediction and the correct result. What should be the difference, okay? And so the distance, okay, or the difference between your prediction or the original input, okay, between your picture and some of the training set picture, okay, defined to be the distance that we can detect. We can detect from the input and the something inside of the training data set. Okay, and so one thing we can do is to try to say, okay, among all the pictures I have seen in the training data set, okay, I compare this picture that I have been given and try to compute their difference because we have the RGB numbers, right? We have the tensor, we have the big, kind of a set of numbers, okay? And we can try to compare each of the pixels to see that how much different, what is the difference between each one of them. And then once we have computed this one here, okay, then somehow we can decide that whether this is something close enough. Okay, so when you have something to compute, okay, with this the actual set of numbers, then we can define what is called the distance. So the distance usually in the machine training, the first one last week we have also mentioned is the L1 distance, which is simply taking each of this picture. Okay, the L1 distance is actually not defining for each individual picture. Each individual picture, we are supposed to come up with this. And then when you have this here, we're supposed to come up to be what is going to be the final score for this particular difference. Okay. And so what we are trying to do is to say that given a set of pictures, we're going to try to compute all of them and sum them up to see that your prediction for all of them with the original, correct the label for all of them, okay? How many of them, how much difference do you get for each one of them, and you sum them up, okay? That would be your L1 distance of your model, okay? So each picture was supposed to give you some values, okay? You can compute the value, for example, in here is by each pixel to be taking the difference, okay? But there could be some other ways for you comparing between the training and the something, okay? So one possibility to be trying to produce the prediction, as we have said last time, is to use the nearest neighbor, okay? Nearest neighbor means that we try to see from the all the original training set we had, all of the original data in the training set, okay? And then if we're given an input, then we try to see that which one particular given training set we are closest to, okay? In terms of distance we have just defined, okay? And if you find the one that is closest to you, then you say, okay, I probably are in the same class of that one. Okay, so if you are, say here, these are the original training data set. Each one of them is a different class. This could be the set of cat, this could be the set of dog, this could be the set of airplane, and this could be something, this could be something, okay? And so here you can see that if you have one input and you need to make a prediction, you simply put that particular dot, say for example, like in here, okay? If you are in here, okay, then you try to find the distance between that and any of the dot in the original training set. And you find the one that is closest to you. And like if you're here, you probably will find this one to be closest to you. So therefore you will say, oh, okay, I belong to this particular class with this particular column. Okay, so this picture here is one nearest neighbor, meaning that we already have the answer for each of these dots here. Okay, and because we are computing the distance between, your input and each of these correct answer. So if your dot fall into some of this location here, if you're in here, and somehow you'll be closer to this or not, so I will predict that to be part of the green. But if my dot is a little bit close, if this one here, then it will be closer to the blue. And so therefore, you will be predicted to be part of the blue. Okay, so this is what we call as the boundary, okay, which is defined by your original training set. So when you have a new input, you simply will put the dot and then see that which particular color it falls into. And if it falls into that particular area, then we will say, oh, okay, it's going to be a green class. Now you can see that here, it has, unfortunately, it has this particular number here, or this particular dot here, actually is the same set as this particular, these numbers, or these dots. But it's actually the correct answer for this one here, unfortunately, is green. And so now you can see that we have this boundary, which depending on your input, if your input is here, it's going to be green. But if it's here, it's going to be yellow. And this is the problem with the run nearest neighbor, is that you need to look at the original data set. And if the original data set somehow is distributed in this strange way, then you're going to have this boundary, which is going to be like this. Okay. Now, the one nearest neighbor, okay, this is what I just mentioned, that, these are the training examples. And so therefore, this is going to define the decision boundary for each of the correct answers. Okay. So the decision boundary between two different classification region is going to be right, like around here. And so if you look at this one here, okay, sometimes that you have some boundary, actually is going to be quite difficult, okay, because it really depending on where your input specificity is going to fall into. And these are, because this area here, actually they are very noisy, okay, we use the word noisy, means that there are so many possibilities, okay, and they are not obvious, okay. And when you have something like this one here, that also that we know the correct answer is green, okay, or in the training set is green, but for most of the reasonable algorithm or systems or human decision, we probably wouldn't say, oh, this should be the boundary for green. We probably would say, oh, this whole area here should be blue, and the green should be just like this, okay. That is because your original training data set may not be 100% correct. Maybe somebody, when they look at this particular picture, actually they label it wrong, okay? So when you try to use the training data set, okay, you need to have this idea in mind. training data set, even though it is supposed to be the ground truth, it may not be the best kind of decision for you to make. Okay, in a lot of systems, you are going to be given data which is in the training data set, but they are noisy. And when you have noisy data, means that they are not 100% correct. Unfortunately, your system will be making decision like this. Okay, and so another way to try to make it a little bit easier for the system and also probably more general is to say, well, let's not just look at one particular neighbor. Let's see that what would be the 3 nearest neighbor. If we have 3 nearest neighbor, then when you are somewhere in here, okay, you will be looking at not just one node, but actually will be also this one and maybe this one or something, and then you try to classify to say that I don't just look at one single source, but I look at multiple sources. Okay, when you have noisy data, the best way to handle noisy data is to say that don't trust just a single. Try to use more, and so that you'll be able to have, kind of more input about the information. Okay, this is always the truth, especially in this day in the social network. Okay, don't look at just one news and say, oh, that's going to be the thing, because there are so many fake news. So don't just trust one. Always double check. Always try to look for some other thing. And so you can try to look, around using 3 neighbors to make a decision. And you can see that in that way, this particular yellow dot now is no longer going to be treated to be one single source. And so therefore, this whole area now. So this boundary definitely is going to be better than this, right? But here you still have the trouble area, okay? And then you can try to say, oh, I'm going to try to make more, okay? And if you have more, k equal to 5, then you can see the boundary now is getting better, okay? Some of the area is not going to be white because we don't know how to make decisions, okay? But, making the wrong decision or something that you don't know how to make a decision, which one is better? When you want to invest into the stock market, buying the wrong stock or not to buy stock, which one is better? It's probably not to buy do anything, right? So the no result, okay, is better than wrong result, okay? So a lot of time that if we are doing the machine learning, that also is the case. Okay, so we have just talked about the L1, which is looking at the absolute distance, okay? But another way is to look at the Euclidean distance, which is to take the difference of that and then square that and then take a square root of that, okay? The difference between the two is that you're going to make the boundary to be not just a straight line, but it's going to be something like this, okay? And this one here, sometimes people think that this is better because you smooth out the boundary to be more, kind of smooth, okay? At least you don't have some particular kind of trouble area which is too sharp to say that fall into the wrong things. And this one here usually is better. So in many of the machine learning algorithm that we use the L2 distance, which is take the difference between the two and then square that, and then with the after the sum, then we take this square root. Okay. So once you define a distance, then we will be able to measure to see how good it is. And the distance is something that going to be defined by you. Okay, whoever is going to be training the system to say, you need to tell me what is called, quote unquote, so-called the distance. So you could be showing this, say, for example, you have a set of articles, okay, and we define the difference between the article. How do you define the difference between articles? Do you compare that character by character? How would you compare between the difference between an article? I mean, all of you, eventually you have to write your thesis, right? When you write your thesis, one thing you have to do is what? Check to see that whether you, you're creating all the content yourself. You're not copying from other things. How do you define the different distance of an article or some report? It's a big area. Okay, there's no easy answer. Okay, you could be using some keywords. You could be using some specific combinations of the words that you use, and or the similarities in something and this and that. Okay, this is still a research area, and people have been doing this. Okay, and so when you do the training, okay, there are different decisions you have to make. What is the k-value you should use? What kind of distance function you define? Okay, and these are what we call as the hyperparameter. These are the choices between the different algorithms. Okay. Last time we have also said that sometimes the data set is not so big, okay, and then so therefore that we would divide the data set, and then to say, okay, we're going to take some of them to be your training data, and some of them to be your test data, and then we can try to, to do something, and we can also split the data set to say some of them to be training, but when you're doing the training, you take a subset of that for your validation so that you'll be able to improve your training, okay? And then after you have done the training, always run it against the test data set, okay? And so this is usually the way that we're going to have when we are trying to produce a machine learning algorithm. We have the data, we have the training data set, okay? And internally, we will try to use part of that to be our validation so that we can see that after we train, we can test ourselves to see how good our model is, okay? After we have done the validation, then we can go back to try to improve the training, and eventually, if we're satisfied, then we still need to give to the outside, and which is going to be your test data set, okay? And in many of the study, they have said that it's better to have the test data set, okay, to be totally separate from the training, okay, so that we can see that the data set you have, okay, really is general enough to be able to facilitate all different data sources, okay, because sometimes the training data set you may have collected is only from some specific area or some specific institute or some specific kind of situation. But if you can have some test data set which is collected from totally different area, that will make your system to be eventually to be more general, okay? Say, for example, in hospitals, even though they are all taking X-ray, okay? But the X-ray pictures from one hospital to another hospital could be quite different. Why? Because the X-ray machines they use could be different. Okay, when you have different X-ray machine, even though they are all taking X-ray, sometimes each of this picture here has specific, kind of bias, or there's shade, or the brightness or something. Okay, and so it's better to be able to separate between them. Okay, and so when you don't have so much data that you can use, okay, then you can simply divide your training data set into 4. Okay, then you try to use different combinations of them to be your validation and do this and that. Okay, so now for our original idea of this image here, okay, we simply say, well, we can try to use the distance, okay, to be able to see that the distance is defined to be the difference between one picture and another, pixel by pixel, okay? But pixel by pixel sometimes may not be the best way for us to be, kind of comparing their differences. Another way to do that is to simply define to say, well, we're going to create some function, and this particular function will be able to take your input to be X, and then we're going to create this W here, which is going to be your model's parameters or weight, okay? And this function here will be able to take your input and use the model here to produce something which is going to be a prediction of your output, okay, or your class in this particular example, okay? So in this approach, then we don't need to manually define the distance ourselves. Okay, we simply ask the computer to say, okay, here, these are the set of my inputs. Try to see that whether you can predict that to be a class. I'm not going to tell you the difference between this picture and that picture. I'm just going to give you this picture, and this is the correct answer. This is picture, this is the correct answer. You find out what is this f is, and you try to come up with a parameter for your function f. This will be even better, right? Because now we are not relying on human knowledge or human idea. We just simply give it to the computer and say, okay, try to do it, okay? And so this is what we call as a linear classifier parametric approach, is that we define this W, okay, which could be something, and then we simply say, okay, we're going to have this original input, okay, and which is going to try to come into this model here, okay, and the X here is going to be, say, for example, this one here has 32 by 32 by 3 numbers, because 32 by 32 pixels, 3 numbers because of the RGB, right? So we have total of 3,000 numbers. Okay, so we just give them 3,000 numbers, okay, as a big vector, okay, to the model. And the model here say you need to come up with 10 classes. So the model here will then try to do the, kind of, you can look at this to be a mathematical computation, W times X. Okay, so if this W here originally is a metric 10 by 30, 72, multiply into 32 by 1, then what's going to be the answer? It's going to be 10 by 1. 10 by 1 is going to be our prediction of 10 different classes. Each of them will be a number. Okay, so if we define the system in this way, okay, we can add also another, function, vector here to be a bias. This is also 10 by 1. But in any case, this one here, the whole thing is going to come out to be the output, which is going to be 10 by 1. Okay, so this, well, kind of jumping ahead, but in general, in most of the deep learning right now, we have all of this in front of this here. Okay, this one here, we'll call them the linear layer. But before that, we have a whole set of this deep learning layers that's going to try to process your original input into something, but eventually we'll ask the system to come up with the linear layers to be able to tell us what's going to be the actual output. Okay, so so this is going to be the situation. Okay, we have the input images. Okay, and the input image is going to be instead of 2-dimensional numbers, it's going to be flattened into one particular vector. Okay, and this particular vector, okay, will then try to multiply this W. Okay, and this W here is something that we're going to ask the computer or our algorithm to come up. Okay, and so you can see that if we have come up with this W here, and then when they take these 4 numbers from the picture, then multiply them together and add it with another one here. This is the bias. This is also something that we ask the computer to try to help us produce. Then we can get another set of numbers, okay, or the vector of numbers. And the numbers here tell us to see that this picture here, okay, in terms of the score for the dog, okay, what is the, how likely or what is the likelihood for it to be a dog? Okay, so you can see that this one here could be something like this, and this one here is this numbers. Okay, and from us human, we look at this to say, oh, this is the cat. But in terms of your model, after you have this and this, okay, you will make the prediction, which is going to say, oh, this is in terms of the score for to be a cat is a negative number 96. This one here is a dog, and this one here is a sheep. Okay. How good are these scores? If you have this picture, okay, and if you just look at the result, how good are they? Not very good, right? Because we know that this one here is supposed to be a cat. So the desirable answer for us would be that your inference, okay, or your prediction here, you want to have a high score to be the cat. You want to have low score to be a dog and low score to be a sheep. Okay, and so, but from whatever is your original W and B, you can see that how wrong or how right are these numbers, okay, or how good is your current prediction, okay? And so from your current prediction and your desirable prediction, then that is when we're going to define, that's your loss function. So the idea of the loss is going to be from some original, kind of random or party trend system. If you produce a prediction, and that prediction compare with the correct prediction, how much difference are there? Okay, how much difference is, are these scores? Okay, and that would be defined in our loss function. Okay, so you can see that we can use the original input picture here, and then we can give it three different W here, okay? And these three different W here, multiply into the input here and with the bias, that will be the way for us to be coming up with the score for the cat, and the score for the dog, and the score for the things, okay? So you can try to look at this to say, well, it simply is a mathematical computation, but you can also look at this to say, well, actually, when you are doing this multiplication, actually, you are trying to compare, kind of coming up to say that the input here multiplied into this one here and this one here is going to be looking like computer is looking at this set of pixels, and it's going to come up with this kind of fuzzy thing and try to see that this fuzzy thing compare with some other pictures, are they close enough or not? Okay, and if your weight here is correct, okay, when you can take this input, multiply into this, okay, then you should see that in terms of that particular cat output, okay, the cat output should have a very clear image. That means that the input here matches the weights, or the weight is just right for the cat. Because everything else to say that, well, I cannot see that to be something. But this one here, if you can look at this one here, and then multiply into this one and come out this, and they are very clear, then it means that that picture and this weight actually is a right match. And when it's a right match, then you should have a high score. Okay, that's the kind of the visual point of view. Okay. Okay, I'm not going to talk about this one. Basically, that there's another way to be looking at how we interpret this this weights. Okay. Okay. So so depending on your original input and also the pattern of your pixels and things, okay, there are some different type of classes, okay, that if you use the what do you call it, the loss function or the distance function, okay, if you try to identify, okay, using this here to say, I want to identify something, okay, to be, like when we look at this boundary of this original training data set, okay, when you have a data set like this or like this, okay, they are actually usually not so easy for the linear classifier using just the simple metrics to do that, okay. We will need to do something more in order for us to be able to identify such patterns, okay? Because you can see these patterns here. It's not so easy for the linear classifier to try to find the things, okay? So we will need to enrich the model, go beyond the linear classifier, okay? But in any case, okay, so the idea of the training, okay, is to try to create this W and this B. If you give an input X, okay, and you have some desirable output that you want to create, okay, and you can see that for each of this picture here, okay, you will come up with a score for each of the class. Okay, so this one here, you can see that, oh, okay, it has a high score for dog, but actually the cat score is 2.9. For this particular picture, you can see that it has a high score for 6 for the automobile, okay, but it has a low score, for example, like a deer or a cat or something, okay. For this picture here, you have the score like this, okay. And so we look at the matrix, okay, or the W, okay, we can compute each one of them, okay, and then we can see that each of this one here, it has a set of score here, okay, but definitely that we have something we say for the cat, we like the score to be highest for the cat, but lower for others. For the car, we want it to be high in here, and then we want it to be low in others. And this one here, of course, right now, it's doing a pretty bad job. It says that this one here is supposed to be a frog, but it's not a frog, and it's a horse, it's not frog. Okay, so the frog score is too low. Okay, so when we come up with the original W, we can look at this and then see how good are the scores, okay, compared with a desirable set of scores. Okay, then we can say, okay, now I want to change my W so that I can do better to produce the scores. Okay, and that's what we do is to say that we can define those functions to let the system know that right now, how good are this, how good are this, how good are this, and secondly is that we're going to try to ask the system to say, can you find a W, okay, which would make this loss function to be the smallest. Okay, that's the job of the machine learning. The machine learning is to try to identify first, you need to define the loss function, okay, and to say that how good are the ones compared with the correct ones, okay, and then, okay, you can try to use that, okay, then somehow we can tell the system to say, I want you to change your W in such a way that you can make the system to be better. Okay. So what we have just done is to look at the scores, okay, and then try to make the system, okay, to create a W, and so that the score for each one of them is going to be matching our correct answer. Okay. Another way to be looking at the output is not so much of look at individual scores, but simply ask the system to tell us to say that this particular picture, what is the likelihood for this to be a cat? What is the likelihood for this to be a car? And what is the likelihood for this to be a frog? Okay, and so another way for us to be defining what is going to be the desirable output is actually not so much of saying that absolute score, but to give us the kind of the probability, okay, the probability to say that this one here is likely going to be a cat, or this one here is likely to be a car, okay? And so one way for us to be trying to produce that is to take the set of the scores produced by the original the f function here or the w here, okay, and then convert that into using this formula here is the sum of all of them with the exponential of the sum of them, and then taken the one with the correct answer. Okay, so if you do this one here using this particular exponential function here, then you add them up and you do the division in this way, then this is going to be converted into this. Okay, but this one here, then we can further convert this one here into this. Okay, then you can see that this is different from that because this one here is giving us the output to say that how good they are to be closer to a cat, how good they are to be closer to a car. But this is going to be to tell us to say that what is the most probability, the highest probability for this one to be a car, the highest probability, the number of probability to be closer to a cat. Okay, so by converting the score using this formula here, okay, and then we normalize it, then we produce this probability. For many of the classification problems, this is a better output than that because this is easy for us to see, okay, what is the best, kind of the prediction right now, okay? But sometimes that when we look at this, these have absolute numbers, but what is the difference between 5.1 and 3.2? The absolute value sometimes doesn't make too much difference. But if we convert that into the probability, then we can appreciate that to say, well, the 87% probability and 13% probability actually is something that 87% is quite significant, better than 13%. Okay, so this is called the softmax. It's converting from the score, okay, from the original score into the your probability. And the softmax, the classifier, okay, is there are also other ways for you to be doing this conversion, but softmax is something that used quite often, okay? And so you will be able to take this probability, and then our correct answer, we want it to be 1 for the cat and 0 for the car and the frog, okay? Then we can compare them. Then it's very easy for us to say that what is the distance between your correct answer and your current answer, okay? But if you look at this one here, it's difficult for us to try to compute what is going to be the difference between your current answer and the correct answer, okay? Because the correct answer, should it be 1,000 to 50 or should it be just 102? Okay, the absolute value doesn't make too much difference. But if we have a probability, then we know that what we want, okay, is the absolute probability, which is 1. And we can see the difference between this and 1, okay? And when we get closer and closer, we can see that here, okay, it's getting 80% correct or is it 70% correct or something. So the softmax, okay, kind of the values sometimes is preferred for us to be using for our training, so that we'll be able to tell the system to say that how good your result is right now. Okay, and there are a little bit different ways of computing, the difference between the two by using different mathematical formula. But basically, the idea is that using the softmax, okay, allow us to be easier the understanding, what is the difference, okay? So here is again is just a simple comparison that suppose that we have some current model, we have input, okay, we have bias, and if we compute using just the pure score, comparing with using the result, which is softmax, then we can see that this one here, okay, how good is the the result right now. Okay, and we can see that if we take this one here to say that, okay, we want the answer to be something, then we can compute and add some number to say, oh, this one here compared with the final result we like to have. Okay, we can have one simple number. But this one here is going to be using some absolute value, but this absolute value is not so so obvious or some easy to understand to have. Okay, so let's try to now see how we can try to solve similar problem now rather than just using the model and the metrics, and whether we can try to formulate the problem and using the solution, what we call as the neural network, or the model itself is called the neural network. Okay, I think all of you have heard of this idea of the neural network many times before. Okay, basically the idea here is that neural network is originally is a bio-neural network, but we try to kind of build our computer systems just like the human bio-neural network. Okay, and so originally this is called the artificial neural network, which is the mathematical model for learning inspired by the biological neural network. Okay, but nowadays when people talk about neural network, okay, everybody's talking about actually artificial neural network, which we build using our computers. Okay, the neural network, okay, is to try to build a simple way so that we'll be able to use the computing power and also using some very simple mathematical formulation so that it is easy for the system to be able to automatically compute the way for it to be updating its W, just like what we have just said. Okay, so neural network in the human neural network, okay, is that you have a lot of these neurons, okay, and between the neurons you have some link, okay, and in the human neuron is that you have some sensors, and the sensors will, be detecting certain signals. Once you detect certain signal, then certain neurons will be triggered, right? And then you pass the signal to the next one to say that I have detected something. Okay, when I detect something, I want to let the next neuron know that here's something terrible or here's something good. Okay, and try to have the information pass around. Okay, so that eventually human brain needs to make a decision to do something. Okay, sometimes maybe in human brain or maybe your muscle. Okay, so the idea here, using neurons to be sensing from your environment, is similar to like we receive some inputs from the environment, and those inputs could be, for example, like numbers. Okay, and we know that just like we would say that, originally last time we would look at the example that I have the humidity, I have the what is the other one, pressure. Okay, using the two numbers. Okay, I have sensed something, and I want the system to decide whether it's going to be raining or not. Okay, so we have kind of used this model before, which is given this x1 and x2 humidity and the pressure, then we can try to have this type of function with W0, W1, and W2, and you can train the system. Eventually, we hope that this will be able to come up with the correct answer, whether it's raining or not. Okay, so using the neural network idea, okay, basically we have, you can say we have two inputs, or you can say we have three inputs, okay, because the third input here is simply a built-in, it's a bias, okay? So we can simply try to have the system to say, okay, if I give you these three inputs, okay, and if you have some model W0, W1, and W2, then I know that you'll be able to make a prediction, okay? And our prediction result, of course, we want it to be say that whether it's going to be raining or not raining, okay? Raining or not raining. So the output here should be, something we want to have a value which is either 0 or 1. And so your input is going to be the W here, and your input is going to be X, and then your W is going to be your model. And when you have the X apply into the W apply into X, then you're supposed to have some output. Of course, that you can try to build something like this, but of course, sometimes that it's probably better for us to be producing the output like this, okay, which is going to be to say that your answer is not always so absolute, okay, because sometimes that your answer could be, something which is likely is going to be raining, but not absolute, because that there's no such thing as you have a prediction which is going to be absolute, okay? Or sometimes that you want your system to say that, well, I want you to kind of eliminate any output, okay, if you have no idea what's going on, okay? But once you know what's going on, then just give the actual value to the output, okay? So just like this is something just like to say that if your signal strength is under something, then don't even give a response. But when you or something have above the threshold, then try to produce the output as strong as your input, okay? And this makes sense in some of the situations, especially like the human reaction. When we detect something, we have a lot of this low, kind of input value, we don't want to respond. But once we receive something which is, above our threshold, then we'll try to respond according to our input strength. Noise, okay, or alarm, okay? When you have something which is, just a lot of noise, then you don't do anything. But once you hear the alarm, okay, then you will try to respond according to the strength of the alarm, okay? And this is something that quite often been built into the system so that your output, okay, can be, kind of from the input, and then you can produce the output like this. Okay, so suppose that we built a neural network like this. So because we have two values, x0 and x1 and x2, okay, and one want to have the output, okay, which also model that to be a neural, okay. So basically, what we're trying to do is to say our neurons will be receiving signals from the outside. One is going to be x1, and the other one is going to be x2, and we want the neurons, okay, each of them to be able to somehow make the decision and then somehow pass some of that information, okay, to the next one. And how much you should pass from here to here is going to be your value of the W. So your model will be defining the W1 and W2. And the W1 and W2 will be multiplied into the X1 and X2, and then they will be given to the last neuron here, okay? And of course that you can have then define this one here, okay, to be your function G. And your G here, you can see that we want our mathematical function here to be G of W0 plus W1 plus, times this one here. And so therefore we can have yet another one, which is simply give this W here without taking any input, okay? So once we build our neural network in this way, then you can see that our system then can try to make this W1, W2, and with a W0 here. And even though it looks like it's very simple to simply say, oh, I have the X1 and X2, and somehow that they are combined together using W1 and W2, it actually is very powerful. So for example, suppose that we want to have built a system which actually is an OR function. Okay, OR function. So we have x1, x2, and we want the output to be this. Or of course is that when you have two zeros, okay, you have your output two false, your output is false. But you have one of them to be one or true, then the output is supposed to be one. So if you have something like this, okay, how do you build a neural network to produce the output? So basically, in this particular case, we simply will decide what's going to be the W of W1, what is the value of W2, because we're going to give 0 and 1 in here, and hopefully our output here will be 1 or 0 according to our something, okay? So if we have both of them to be the way here to be 1, okay, then you can see that actually this one here plus this value, if we put this one to be -1, you actually will produce a function like this. Because in this one here, we put a way to be 1, 1 here, and give this one to be -1, okay? Whenever we have x1 to be a 1, or x2 to be a 1, okay? Then we will have the values here to be 1 or 2. Okay, and because we have -1, so therefore you can see the output here will be either 0 here or 1. Okay, and so if both of them are 0, okay, using this particular, so it will be 0 here, 0 here, and put that into this. This is going to get zeros, even though these are the weights are 1, it's going to get zeros from these two links. Okay, and then this one here is going to be -1. And when you have this one here to be -1 here, you can see that when you're looking at this one here, it says that I'm going to give you 0. Okay, so this G here is defined using this particular step function. Okay, and this input here, they are configured in this way. Then you will be able to see that when both of them are 0, then your output will be -1, and which actually using the step function here, you will be 1. You will be 0. Okay, but if any one of them change to be 1, okay, then immediately this one here come out to be 1. If both of them are 1, again, it's going to be 1. So therefore, this will implement exactly our OR function, okay, using a neural network, okay. The same thing we can do for the AND, okay. When we have AND, the difference between the AND and OR is that only both of them, the input is 1, then your output is supposed to be 1, okay. So for this one here, we're going to build a neural network to be -2, okay, using this one here, okay. And the rest of the W is still the same. And you can see that in this case, only both of them are 1, and because this is -2, so therefore it's going to be 0 here, and which is going to map into 1, okay. Anything else, when you have 0 on either side, then this one here will be, less than -2, and so therefore you will be shown to be 0. Okay. So suppose now we come back to the question. We have a humidity and we have pressure, okay, and we want to know what is the probability of the rain, okay. So basically, the idea here is going to be try to have system to try to put the weight W1 and W2 here, and then you also have the W0 here, okay, and then try to see that, okay, your output here, which is going to be your particular number here, is that matching our correct result or not, okay? And if your output is not matching your correct output, then the neural network, next time we're going to talk about, say, it's going to try to say, oh, your answer and the correct result, how different they are. And we can use that to try to go back and to try to update each of these stuff here. And that will be the back propagation that we're going to talk about next time, okay? So I'm going to stop here today. Again, sorry for being late today. I have to, do other business, but next time we'll, try to finish our discussion of the neural network. Okay, I'll see you next week.